Capstone group. We have the Conehead group working with Goodyear. So take it away, guys.
How are you doing, everyone? Thank you all for being here. My name is Jesus Campos. These are my associates.
Brennan Barnhill, Christopher Miata.
And Mason Cave will be joining us shortly. This is our senior design project for Goodyear. I'll go ahead and start us off. So just a bit of an overview. We'll give you an introduction of our client, Goodyear. We'll show you what our scope of the project was, our design proposal, our selection process, and then break down the systems within our design, go over some analysis and testing that we did, and finally our results and conclusion. Now I'll be handing off to Mason.
First, we'll start with our client information. So for this project, we're working with Goodyear Proving Grounds. It is the largest Goodyear tire testing facility in the U.S. and it has over 7,000 acres of land outside of San Angelo, where they have a bunch of tracks to test tires, some of which are just asphalt pads where they lay out cones to provide test tracks where they can test a car's mobility with tires and the traction the tires have. So why are we So currently for the cone placement process, the operator will load cones into a golf cart, and you can see in the back there, that's where they'll keep the cones, is in that bucket. They drive to the test area, they remove a stack of cones into the footwell of the golf cart, and they will individually drop each of those cones off of that stack as they are going around the course onto the designated spots to make the track. And once they run out of one cone stack, they will then pull another cone stack from the bucket and place it in the footwell and continue until the course is finished. So next, I will hand it over to Chris to talk about our scope.
So for the scope of for this section, I'm talking about the problem, what issue we have to solve, and how our design process. So what's the problem? With the operator, there's a great ergonomic risk while laying cones. The operator is twisting and turning while grabbing the cones, and that could lead to fatigue in the hips, backs, shoulders, and we don't want that for an operator. So how do we solve this? We first broke down our project into two deliverables: our project design strategy and our cone delivery system. Project design strategy consists of the identification of our subsystems, the creation of a multi-year capstone plan, a cost estimate, and a product design. For our second deliverable, we went with the cone delivery system. That cone delivery system is going to reduce ergonomic risk, going to be within the 800-pound loading limit of the golf cart, and be able to lay out the cones in the track within a 45-minute time constraint. That 45-minute is about the average of what it takes to manually place the cones. Then it also has to adhere to Goodyear's lockout tagout procedure. For our multi-year capstone plan, we laid out 4 years. Within these 4 years, it will achieve fully autonomous cone dispenser. Our capstone focused on the pure dispenser of cones to the track. This would be strapping the cones and being able to implement a self-loading system. So that system would feed those cones into the dispenser. The next year would then focus on reversing that system, retrieve the cones from the track, and be able to load them. And then the capstone after that, the third one, will focus on automating both the retrieval and the dropping of the cones. This would only leave the driver to just focus on driving the track, and the cones will drop on their own. The final year would be a fully autonomous self-driving vehicle, which would eliminate the need of a driver. Now heading over to Bill.
Hi, so with the given problem and constraints that we have, we started to brainstorm and come up with the original ideas for how we would go about solving this problem. These are our initial sketches of the 3 designs that we proposed. The first was the claw and robotic arm. This is kind of the grabber arm that you would typically see in an arcade, where there would be 3 degrees of freedom, and the grabber arm would grab the cone off the back of the golf bed, rotate, and then drop at a set point. The mechanical column was our second proposal. This one is kind of like a submarine where you have 2 doors, the inner door and the outer door. But with this one, it's the lower jaw and the upper jaw. So you have a column to support the stack of cones. The stack of cones would fall all the way into the bottom jaw. And then the top jaw would close, in which the bottom jaw holds only the bottom cone, the top jaw in which holds every other cone above that. So the bottom doors would open, dropping the 1 cone, close, and then the top one would open, reset the bottom jaw. And we would repeat this process until all of the cone stack was dropped. The third is also a column, but it has a pinwheel on the bottom. The pinwheel is what we call it. It's really a gear. And so there would be 2 rows of gears that would support the column and all of the cones in the column, and each tooth would hold a single gear. And as the gears rotated, they would drop 1 column at a time, depending on where the tooth was in position. The mechanical column and pinwheel system required something to load the stack of cones into the column for it to be autonomous. So we designed a self-loading system, which would replace the standard golf cart bed, and instead we would replace it with these rollers, which would operate under a motor, rolling and conveying the stack of cones into a passive ramp. The passive ramp would then transition into the column. Now I'm handing it off for design selection.
So we have a few alternatives for our design. We had to make a decision, and for that we have our design selection process. We have different criteria to make a decision on which design to pursue. For each design, we looked at some qualitative criteria, including the consistency, where we rated the consistency of each design by looking at the movements that the cones would need to make. The ergonomic stress is another qualitative criteria. We estimated the number of movements, twists, and turns that the driver would have to make for each design. The time efficiency, we estimated the time it would take for each step in the process of each of these designs. On the quantitative side, we have our costs. We prepared a preliminary material list for each of these designs. We estimated the costs, and additionally, we used that to estimate the weight and the power for these components. This is our final design matrix. So we rated each factor on a scale of 1 to 5, 5 being the best overall. As you can see, the best overall score was for the pinwheel design, which has the biggest victory in consistency and time efficiency. So it would be the most, we estimated it to be the most consistent design and the most time efficient. This is our initial cost estimate for the design. So as you can see, the most expensive portions are the self-loading mechanism and the column. This is largely due to the quantity of materials that you needed to build these, and also due to the motors and motor drivers. Now I'll be handing it off to Chris for our design overview. Brandon, please.
The design overview, we have broken down into several subsystems. We have the frame, the column, pinwheel, self-loading mechanism, ramp, the motor subsystems, electrical, and controls. So all of these interact together to encompass our entire system. For the frame design, I'm going to hand it off to Mason.
The frame design, this was the core structural system in our design. It was made to support the self-loading system on this bed here, and then the ramp on this bottom structure here. So it will hold the rest of the system in place, and it attaches to the golf cart to ensure that all the systems will be structurally held together. Next, we'll move on to the column. The column is what holds the cones as it's being dispensed. So you can see here that we have an opening where the cones would enter in order to properly transfer from the ramp into the column. And then we had it held in place by these steel angles here. Next is the pinwheel. So this was the design for our pinwheel mechanism. It's a 3D printed gear that would attach to a shaft, and as it would rotate, it would dispense cones one by one. So one of the key things was trying to determine the pressure angle on it, because we wanted to ensure that it would get a good hold of the bottom of the cone, and it would separate the cones from the cone stack, and it would drop the cones one by one. Then we have the motor subsystem, where the pinwheels would be mounted on to these two shafts. And so the motor subsystem, this is what gives our pinwheel system movement. The motor will transfer movement into the two shafts here. And so this system, what it does is ensures that both shafts will be rotating evenly in opposite directions, ensuring that we get consistent opposing rotational motion. And this will give us the means by which we can drop the cones one by one using the pinwheel system. Next, I'll hand off to Chris to talk about the ramp.
So here we have the ramp. This ramp serves as a transition from the self-loading into the column. It was designed to work as a passive ramp on the second slide. This ramp is consisted of rollers. Those rollers will catch the cones from self-loading and pass it the slide goes into the column. The extra support shown here is so that we could be able to attach the column to the ramp and it serves as a structure. Then we move to self-loading. This self-loading mechanism was designed to transfer and deliver the cones to the ramp. There's a motor that actuates a inline shaft. That inline shaft then, with the help of split spools, the split spools are these red spools down here, and the inline shaft moves the split spools, and those split spools, with the help of the polyurethane O-rings, transfer the motion to the groove rollers. This allows the smooth transfer of cones, since we have initially designed for multiple stacks to be on that bed. It will move each stack passively. And then the stacks are loaded from one side, and with the activation of a button, it will move one stack into the ramp, only if that ramp senses that it's empty. I'm handing it over to Brendan.
For the electrical system, we took in a couple of considerations. The first was for the user. We wanted to make sure that it was an easy operation, and we thought about the maintenance required as well as their overall safety. And the environmental considerations were atypical. We were in a golf cart, so there would be vibration, there would be movement, and there would also be water. So Goodyear has both a dry track and a wet track to test tires on, and on that wet track, there could be potential for water to get into our electrical system, which would be bad. For the electrical system, this was our overall flow chart that we used to connect each component to its counterpart and kind of comprise the entire system. So this is broken up into power supply, sensors, the microcontroller, the actuators, and operator interface, and kind of just gave a groundwork for what we would be building upon. The first thing that we looked at was the power supply. The power supply starts with a 24-volt battery. This is a lithium iron phosphate battery, which is a newer technology. It's not a lead acid, and it allows for any orientation. It's also waterproof. This is going to power our motors, which are those big things that require a lot of electricity. This system also includes more sensitive electronics like sensors and buttons and lights, which would need to be stepped down from that really high voltage. So we use a buck-down converter to step down from 24 volts to the 5 volts, which would allow those sensitive electronics to run. For the lockout-tagout procedure, we use a circuit breaker. This circuit breaker, if the battery overshoots and provides too much electricity and will end up frying the components downstream, will automatically break the circuit physically and save those components. But more than that, you can manually set it and physically disconnect that sense system and then lock your electrical box And that way, this compliance standard of safety is that it's de-energized throughout the system and it's locked in a safe position. For our sensors, there's a variety of sensors that we used. The first in the design phase was the time of flight sensor. This shoots an infrared beam to hit a component and then measures the time it took to bounce back and receive. And this is to measure distance. We were initially designing it to be placed on the end of the golf cart bed and measure how far the cone stack was from the passive ramp. That way we could tell how long the self-loading had to roll the cones into this passive ramp. However, in manufacturing, we found that this specific sensor was redundant and it was just adding complexity, so we omitted it out of scope. The second is the infrared IR brake beam sensor. This one is kind of the same sensor that is in your paper towel dispenser in the bathroom. So it has a consistent beam. When it's broken, it sends a signal. So this one we use to measure the cone stack presence in the passive incline. And if that is absent, then we go ahead and hit that self-loading machine to roll them into that until there's presence there. The second place that we use this infrared sensor is at the very bottom of the column in the pinwheels. This confirms that there's a successful drop and allows the machine to continuously go, and also gives information for the operator that there was a successful drop. The last one here at the bottom is called an encoder. It's used as a homing device for the pinwheels. So at the start, when the machine is turned on, this is a device that allows for the microcontroller to account for the position of the gears at the very beginning. Because those gears can be in different positions at the start, and so if they're in a different position and we don't account for that, then our drops would be inconsistent. The microcontroller that we used was the Arduino Mega. It has a variety of pins that are both digital and analog, and has enough real estate for further capstones to add on to this. Secondly, there is an open source platform through the Arduino interface that allows us to see existing code from previous projects. And third, it has both the digital and analog pins, which we would need both. Some of the operator interfaces were a momentary push button that would allow for just the go, some indicator lights, and then e-stops. These e-stops don't go through the microcontroller, so they don't go through the electrical system itself, but they physically disconnect manually as a safety precaution. We also have to have motor drivers for each motor. These motor drivers act as the bridge between the microcontroller signal and the motor. So they take the signal from the microcontroller and they apply a specific current to each motor to allow for them to turn. They require both to be compatible with the specific motor used as well as our electrical system specs. Now we will move into analysis.
So some analyses that we performed in our design phase was first determining the motor torque requirements. So we used the following formulas to determine how much torque the motors would need to supply in order to both support the cones as they were being dropped, and then the amount of torque that would be required to rotate and drop off a single cone. So that was determined by this top equation, and then the bottom was for the self-loading to determine how much torque was needed in order to move a bed full of cones into the ramp, or be able to provide that motion for it. And so, second analysis that we did was performing an FEA analysis, or finite element analysis of pinwheel shafts. So, in order to determine if our shafts could withstand the weight of the cones, we used this analysis to determine the maximum stress and deformation that it would be subjected to under a full stack of cones. So you can see here that we had some assumptions and boundary conditions, that being that the shaft would be assumed to be supporting a full weight of 20 cones that would act evenly on each pinwheel as it was connected to the shaft. And the boundary condition is that each of the shafts will be supported by pillow block bearings. And here are the results we had. We determined the max stress for the FEA analysis to be 2.8 megapascals, max deformation to be 0.82 microns, and that gave us a safety factor of 15, which is the maximum that the ONSYS software could determine. And part of the reason why we think this is so light is because of the stainless steel yield strength, which was 200 megapascals, so that gave us a lot of strength as far as the results go. And now I'll pass it to Brandon for FEA analysis.
So we also did FEA analysis on the gears, and our purpose for this FEA analysis was to determine the appropriate material for the gears. We were hoping to get away with a 3D printed material for the ease of manufacturing as well as the ease of replaceability. If it's a metal gear, then those would be either difficult to find and buy and deliver, or difficult to manufacture. We assumed that there would be a full cone stack, so 20 cones, and we did the test only on one gear. So in the actual device, there would be multiple gears, but with this one, we did a full cone stack onto one gear to just show the extreme case. We did the material in PLA and ABS with a pin support in the center and then a vertical force. In the analysis, we yielded as well, similarly to Mason, a safety factor of 15 for the 3D printed material. We had a max stress of 2.45 megapascals and a max deformation of a fraction of a millimeter. So with these findings, we assumed that it was appropriate to use that 3D printed material, and that assumption was further validated in testing as well as manufacturing. Now we'll move to testing.
So with our design, there were several assumptions that we made. In order to make sure our design would work, this is what our testing phase was for. First test we had to determine was the sliding angle for the ramp. So the National Institute of Occupational Safety Hazards determined that you use up, that employees should not lift a load beyond their shoulder height. So that limits our incline on the ramp, and in order to meet that requirement, we needed to ensure that the angle would not be too steep on this ramp. We initially estimated a degree of an angle of 10 degrees. With this test, we were able to determine that this angle is sufficient for the cones to be led down the ramp with only gravity. There were a few other key findings from this test. First is that the cones would get stuck in between rollers. We originally estimated transfer guards. We had to add to that design a conveyor belt. Additionally, we have this guide right here, which allows the cones to, prevents the cones from tilting this way when they're being dispensed from the ramp. Next, we have the pinwheel assembly. This is the mechanism that's actually dropping the cones one at a time. We prepared this test bench, and we determined that the design for the pinwheel gears was sufficient to dispense one cone at a time. Additionally, we verified the spacing in between the shafts to make sure that this wouldn't be too much or too little for the cones to fit in between. We also have a cone separation test. We had a concern that with the old cones that they would become stuck together and the driver would have to separate them. As Goodyear is phasing out those old cones with new ones, we were able to test the new cones and determine that they do separate. Finally, we have the ramp to column transfer test. With this one, we're verifying that the ramps is able to transfer the cones smoothly into the column. With this test, we found that with the current design, there isn't enough spacing in between the ramp and the column for the cones to slide smoothly in. There's currently a problem with the cones, the column obstructing the cones from sliding in. Now we'll be moving on to manufacturing.
So during manufacturing, we implemented several changes to our designs as we were building it. So the first thing was to the frame. We added an additional support to the bottom there that was not first in the initial design. And this support had spacers. So the reason we implemented this was because the golf cart, it had it has a textured bottom on the base where the frame would be sitting. And so because of that, we needed those spacers to ensure that it would rest off of the base. And then the second change we made to the design was altering the angle of these two angle pieces there. That ensured that we did not interfere with the lip of that golf cart bed. Then in the motor system fabrication, we applied some tensioners to the design. This is to, one, get us the consistent opposing rotational motion, and also it helps to ensure that the roller chain is taut during operation and it's not going to be loose. Then we also made the addition of adding some sensor mounts to either side, and this helps us to determine whenever we have a successful cone drop. Next was the ramp design fabrication. In our initial design, what we used was rollers using transfer guards. So the idea here was to allow for smooth motion with those rollers. But unfortunately, in our application, what we found was that these transfer guards, they would catch cones, and it would not allow them to roll at the 10-degree angle that we needed. And in part, whenever they were used, they increased the friction between the rollers, which made the rollers harder to move. So to counteract this, we used a conveyor belt instead, and this improved our the mobility of the cones as they were transferring from the ramp to the column. And then we also made the addition of guides on either side of the ramp itself, and this is to ensure that the cone stack is as straight as possible as it is moving from the ramp to the column. Now I'll hand it off to Chris.
With self-loading, we originally added the triplegious stack as well so that the cones would not fall out. We decided to cut out a hole on that side so that the operator could load and have a specific place to load the cones. Allowing us to choose where the operator is going to load the cones made it easier for us to choose the location of the E-stops. The reason for the E-stops is because since the rollers are going to be in motion, we don't want the operator to get his fingers crushed. And to avoid that, we added a E-stop right within arm's reach so that he could be able to stop it if anything were to get caught there. And then
For the electrical system, like Mason's said previously, there was a couple of changes that we had to make simply because there was a pretty big learning curve going into it for electrical work. So for the power to be outsourced into all the various components, we had to use those two power rails that we talked about, the high electricity and the low electricity. Those were done with screw terminals and the power blocks. This was used instead of soldering to allow for the vibrations. The screws would handle better. They'd be able to be maintained a little bit easier rather than the solder. Similarly, we used quick connects instead of solder. These quick connects would be crimped or crushed around the wires, and you can plug and play with them. Rather than having to take two wires and solder them together, the solder also creates a very brittle material, so in vibration, it's liable to snap. For the shield board, for Arduino, we had purchased all these components without necessarily thinking about how they would be connected to one another. With these, we had a solution for the connection, but it didn't originally fit. So we had to get this later on, and it's a shield board that goes right on top, and these are all of the pins. So this is a place where the command wires could be inserted. You would just screw on top of that, and it would shut that gate, and then you would have a connected wire without having to use solder. Again, easily maintainable for the operator, and so forth. Some additional considerations in the power system were Anderson connectors. A 24-volt battery is about the size of a car battery. It is the most dangerous component of this. And so if you were to have to power on and off your circuit, With the ring terminals, you would be putting your hands pretty close to those electrical voltage terminals every single time. But with the Anderson connector, you can just touch those plastic components, and the ring terminals on the ends could be permanently connected to the battery. This way, the battery charger, the battery, and the circuit all have the same plastic component that you can just unplug one and go plug in the other. We also added a battery box and the e-stops for, again, additional safety features. For the 24-volt voltage regulator, this is an added component that we needed during manufacturing. And that was because originally I decided to purchase a 24-volt battery. And I assumed that a 24-volt battery was going to be 24 volts. So I told Mason to get a motor driver that was with 24 volts. A battery can go from, a 24 volt is a nominal term in a battery. It actually goes from 28 volts to 18. That 28 volts exceeds the limit for that motor driver, and it would have fried it. So we had to get a further component as a voltage regulator to output that perfect 24 volts to that driver to maintain functionality. And there were several cases in this where we had to buy additional components to continue our functionality. Moving on to controls.
So right here on the right, we have our control panel. It includes 3 LEDs and a switch toggle. The switch is used to power the system on. It will shine a light when it has power connected. So as long as the battery is plugged in and there's no e-stops connected, the switch on the right will be lit. The red LED will light when there's an error. With the error, it won't reset until power has been reset. The orange LED will indicate that the self-loading system is in motion, and the green LED indicates a successful cone drop. So this is a look at our system software. The programming is divided into various modules to help organize the functions that are required to make these systems work together. So on our input side, we have our sensors, buttons, and switch. These go through their own individual module and into the main. The main is what processes these inputs and determines what output is required. The output is the motors and the LEDs. The system uses a state machine, which is what you can see right here. The 3 states that the system can be in are idle, running, or error, and there's a few conditions for transitions in between these states. The switch will determine if it's in running or in idle, and when an error is sensed, the system will go into error state from either idle or running, and the system can't transition back from error to idle or to running. This is a safety feature, and it requires the power to be reset before operations can continue. Now we'll be going into our functionality test.
So, for our functionality test, what we were doing is we were trying to test how the whole system would operate. And so what we did was we set up a course outside the Vincent parking lot so that we could test how well our system would perform in being able to dispense cones, how the self-loader would transition to the ramp, how the functionality would work. And so the goal of that was to identify what systems were functioning and what changes might need to be made to it. So here we have a video. What?
Just go to the view.
Okay.
doesn't seem like the video's working.
Okay.
So you'll look again.
Okay, well, we had a video here where it showed us dropping the cones, so now it's just a picture of me driving it. But we can tell you, it can dispense the cones. One of the issues that we saw, and that was in the video, was that at one point it dispensed 2 cones, and part of that error, we think, was because there was a misalignment with the shafts, because once there are cones resting on the pinwheel gears, there's some amount of slack that exists within the roller chains. So whenever it's under load, that slack just moves one side down a little bit more, and that causes a misalignment. We believe that caused a misalignment that would cause multiple dispensal of 2 cones on a single button press. But here are some other results that we had from it. So the self-loading mechanism delivers cones to the ramp. We had consistent transitions from the self-loading to the ramp. The subsystems are independently functional, and the pinwheel system can drop cones upon button press with minimal delay. And some of the problems we had was that the transition from ramp to column cannot consistently control cone motion. So as the cone stack is moving from the ramp into the column, we can see several things. One is that the cone stack will just rest on the wall of the column, and it will just be stuck there. The other is that as the cones are moving, they will separate and they will drop to the bottom, but it cannot consistently land on the pinwheels themselves. And so those are both issues that we are seeking long-term solutions for. But then, as I talked about the pinwheel misalignment, and that we believe that was due to the roller chain system, and then we think that also another implementation that could be made is that the pinwheels, there could be use of additional pinwheels to ensure that there's more surface area in contact with the bottom of the tractor cones. And then some of our sensors had trouble indicating when cones were present in front of the IR brake beams. So here are some of the future improvements we hope to make. So one is to modify the pinwheel gear design so that it will have more surface area that will get under the cone. Add additional pinwheels to shaft for more control. Adjust the roller chain to improve pinwheel shaft alignment and improve sensor functionality. And so long-term improvements are to include some ramp to column improvements to the ramp to column transition, such as using like horsehair brushes to slow the cones as they're transitioning, and then like separate and drop onto the pinwheels, and hopefully get that more consistent. And then implementation of a mirror for a driver's convenience as they're dispensing cones. So this is an improved cone placement process. So now the operator can push a button to dispense cones, and
So rather than having to place each cone by hand manually, all the operator has to do is press the button, and the column will drop 1 cone at a time. The loading is done by the operator after the retrieval. We have the side location where we are loading the cones, and the rest is all operated by the machine. So this machine handles the dispensal, and the operator needs only to handle the retriever and the loading.
So to conclude our machine, we will take a look at the project deliverables from the very beginning. And our first semester of the design phase, we correctly identified subsystems, we created a multi-year plan, we had a product design and a cost estimate. In the manufacturing system, we did adhere to the 800-pound loading limit as well as the lockout tagout standard. However, the total functionality isn't 100% consistent as of yet, so we cannot say that we reduced ergonomic stress, nor did a 45-minute time constraint. The condition of the project, and it's hard to see without the video, is that all of the subsystems that we manufactured on their own function great independently. However, when we put them together, it was the transition from the column to the ramp, or the self-loading to the ramp, and those in-between transitions that we had problems. And that testing was conducted a couple weeks ago. We have ideas and solutions to mitigate those, but that would take ordering more materials and doing further work. And so the total functionality of the system is on the horizon, just not done quite yet. For acknowledgements, we want to thank David Gradley for all of his help in the manufacturing. His advice on safety as well as just his experience in manufacturing was very valuable to us. Mike Brasher was our main mentor throughout this entire process. He helps with just general project management, teamwork, how we talk to a client, how we break out work and break out a project of this scale into actual doable steps. We talked with Paul DeSello and the Goodyear team, and they were very welcoming. Every single time that we've been down there, they were very kind to us, and they helped in any way that they could. Manuel was our trailer. We needed to grab the golf cart from Goodyear. He kindly and was very generous to let us use his trailer to do that. Dr. Manuel Garcia helped us with the FEA and all of the CAD analysis, and our Capstone peers gave us feedback every week, which was very valuable to us. So we wanted to thank these people specifically, and thank y'all.
Any questions?
So what's the chance of error?
So with our system, there's errors between the ramp to column, and there's errors with the dispensal dropping 2 cones, which we found in our functionality testing. So those are the 2 biggest obstacles for 100% functionality.
So you don't have a chance of error?
The chance of error right now between the ramp and column is about 50%. The column itself was about 20% based on our test results. So every 5 cones, the column would drop 2 instead of 1.
So your observation that I guess key sources of errors that were actually in the transition between the subsystems was really interesting. I think lots of engineers find out that's where the problems are, right? So I'm really pleased that you found that. But my question is, with that, so knowing that and the issues that happen at those transitions, would that cause you to reevaluate any of your subsystems themselves and maybe take a completely different approach in the subsystem because of what's going on in the transitions?
Yes.
And if there's one in particular you want to talk about, it'd be interesting.
Primarily the ramp is the biggest one. We decided on a passive incline to avoid having to add motors, cost, and complexity to the design. It's gravity powered, so it's nice that you can rely on gravity, except that the cones don't exactly behave the same way every time.
We lost control, and when we lost control, we didn't do the testing that we needed because we didn't have it assembled yet. So we couldn't test the exact conditions, and we had no control over the actual outcome. So that's where we did a mistake.
So you probably would have done an active system or something like that
An
for
active
the
system.
That or simplify the design to not have as many transitions in the forefront.
Mhm.
And one reason why we were trying to go with a passive design during our design phase was we were looking to source our motors from one particular motor supplier, and it was pretty expensive for every motor that we were looking at getting. And so thinking about it, using an active system there did not seem reasonable to us at the time, but following the next semester, we were able to find other motor suppliers, in part because we couldn't get the supply from those original suppliers from the first semester that we were looking into. And if we had known about them, then we probably would have considered an active design rather than a passive system as well.
Interesting.
How bright are the lights?
The lights are,
Sorry.
I don't have a number for you, but they're viewable for the driver. During our functionality test, that was one of our observations.
So I got those lights off of a place that uses them for things like jet skis and that kind of recreational stuff. And they're meant for do-it-yourself projects in that regard. And so the functionality was pretty reasonable in testing. It wasn't distracting, it wasn't too bright, and it was still visible. I don't have the exact number count for you.
That was a concern we had with the bright sun but, we did the research and got the right ones.
How was the design fitted to the golf cart?
How was the design
Fitted to the golf cart?
fitted to the golf cart? So, the primary part for that is the frame. That's fixed to the golf cart using bolts, and the golf cart already has mounts for the original, cargo bay for the golf cart. So we used those same mounting points for the frame, and everything else was fixed to that frame.
Doing that allowed us to build the frame and know that it fit, and then we could just add our things onto the frame rather than having to put every single thing directly on the golf cart. It was one of the better things we've done.
Someone have a question?
What's your takeaway? One takeaway.
Chris?
Better dimensioning. We lost a lot of time, especially with the frame again. We didn't take correct dimensions and it messed up with our tolerances. We had to re-weld our frames and a lot of the holes misaligned. It's just, we needed to document all the dimensions better, take better dimensions.
No other
And
problem
that's a
there.
big one.
My takeaway is the magnitude of the scope of a project like this. There's so many things that go into it that you wouldn't realize, like delivery times, or things not coming in right, or the connections to the electrical components. All of those things have to be accounted for in the planning phase. If not, then you end up in bind. And we ended up in a bind because we didn't account for those things. So knowing that now, I would probably reduce our scope slightly to ensure that we get a 100% final product at the end.
My takeaway was with well, there were several, but my biggest one was with the electrical system, working with the programming and all of the different components. I showed a diagram of our inputs and outputs, and it seems like, oh, there's 4 on each side. It doesn't seem too complex, but the actual programming and testing for that took a lot of time that we were not prepared for.
I think one of my biggest takeaways was was sourcing your materials. So with the motor, we had a lot of trouble early on in this semester with having to look into different suppliers. One was because some of the items were not in stock, so then we had to switch to another supplier. And then we then had issues with our initial supplier because they were planning on delaying the delivery of one of our components till like April, and that was just not going to work for us. So there's a lot of learning there with what supplier you should look to use.
And designing for flexibility as well. If we can get something that can encompass a couple of different things, like the motor driver is a great example, right? We got a very specific 24 volt, but there was the second motor driver that we used had a very massive scale. You can use any of these voltages. Getting things like that allows for flexibility in the future for those kinds of unknown outcomes.
So you mentioned the 45-minute time limit. Is that, you mean 45 minutes to set the cones?
Yes, so
Yeah.
as it stands right now, there's a Goodyear employee who drives every day, and it takes him about 45 minutes to an hour to complete the
To
entire
set that
course.
up, yeah.
And then later on in the day, he goes and takes it back up again. So we were hoping to do that, and for it to be productive for Goodyear, they would want it in about the same time range.
Right, so if the machine is too expensive, then the time value for like using the machine, if it's only gonna save you 45 minutes or
Mhm.
an hour and a half, then it exceeds that value.
Yes, sir. So our 2 things that we were looking at was the ergonomic stress and then doing the job, right?
Yeah.
There was a previous Capstone, the drone, and they were, I'm pretty sure fairly functional, am I correct, Paul? But their problem was that they were too expensive.
Yeah.
So
Yeah,
this was an alternative solution to something like that.
yeah. That makes sense.
That previous Capstone ended up estimating the cost of an injury at about $100,000. So if you can avoid that injury, even if it's once every 5 years, there's a pretty good payback.
Yeah,
So I don't know if I missed it, but how long does it take to empty out the column?
That depends upon the cones that you're setting. So their track is dependent, it's not just one cone every 5 yards. Oh, go ahead.
I meant like with your testing, because y'all did it, right? So did y'all
Yes.
measure the time for that one? How
And
long did that
that's,
take?
so our cones weren't consistent. So we had some long, some very close. And so we don't have an accurate estimate to that because it's dependent on
The errors that happen.
the amount of times we're placing the cones and the time.
Yeah, so not the errors, but the tracks have different spots where the cones need to be placed. Sometimes they're 5 feet apart, sometimes they're 20 feet. So the column on its own, if you just sat there and just click the button takes less than a second to activate and dispense a cone. But it's getting to the spot and positioning the cart that takes time.
So what was the issue? Because they were delivering 2 cones at the same time. What was the problem, do you think?
That issue is because of the gears right now. They don't have enough real estate, so when the cone lands on the gears, the teeth are too small, so they land unevenly, or some are, they push past it because they drop too hard, or something like that. So we're not controlling the land of the cone, so they are uneven in the drop. And then as it rotates, potentially 2 cones slip past.
This
So
is
what
what,
would be
like,
the solution?
this is what I'm wondering, like, for your, one of the systems you do had a basically active control of the separation of the cones. So I was wondering if, when you come back at this, you say, well, you know, in our current analysis, this was the top one, but now if we go back to the reliability, looking at the things we've learned, maybe that other one's a better solution.
We talked about it before.
Yeah, so, very interesting project.
So one of the proposed solutions we have for the dispensing of the cones is increasing the tooth width on the pinwheel gears. That should give more surface area between contact between the cones and should improve the consistency. Our initial testing, as you saw, was with a wooden assembly and not too many cones. When you put the full stack on, it's a lot heavier. And so we were limited by having to manufacture and then iterate on that manufactured design.
So one of your original deliverables was scoping out the multi-year project.
Yes.
Sounds like, Brennan, you would reduce that scope?
Yeah, so I would make the self-loading, that was, I think, our biggest thing, because we shouldn't have included the self-loading. We should have just focused on the disposable codes, and we still could have hit that 4-year timeline by moving that second year to self-loading, or second year to be retrieval, third to be self-loading, fourth to make it autonomous completely. And we still could have had a pretty complete project doing that scope.
So you could have just done the traffic cone dispensal, and then the magazine could be some other
Yes.
Capstone's problem. Gotcha.
Sorry?
How heavy is the entire thing?
Basically, I added up all the weights of all the components, it came out to about 250 pounds in total.
For the manufactured systems, the cones is added on top of that, and of course the driver is added on top of that.
The cones is about 200 pounds, and then the driver, we assumed 250, so we were still underneath that 800 pound.
In those early design phases, did y'all ever realize y'all were like over-engineering it and then decided like simpler design would be better?
I think that's what they're called. You know, that was the one that we decided was over-engineered. That's the main one.
A lot of the things where we were observing like over-engineering was in the design phase when we had some pretty lofty goals there. So after, like it was usually after a lot of discussion, we would tend to scale down our scopes of things that seemed more manageable for our team. Does that answer your question?
Yeah.
Not directly, but in the same vein, I think so those 3 design proposals that we did, we made a deal in, so bill of materials, we did a cost breakdown, and all of that, for all 3 of those plans. So we spent a long time on all 3 of those, and we only picked one of them. So I think pulling the trigger on that decision a little bit quicker and simplifying the methodology of it would be that. I think we over-engineered in that method.
Following a little bit with John's questions, like the structure, for example, do you think it's, you can make it lighter?
Yes, so you want to talk about it? We had a decision between steel and aluminum, and steel was a lot cheaper, but much heavier. And so we talked with the client, and they preferred steel over aluminum. But in the original design, we had aluminum as that material.
Okay, but that's material, but then the thickness of the steel, could you reduce it and still have?
So for the self-loading, mainly the C channels, whenever I went to choosing those materials, I did make the mistake of choosing it too thick, and that's what added a lot of weight for the self-loading. So I know that we can reduce the thickness of that one.
Did you do any calculations about?
part of that came from time constraints. We spent a lot of time designing 3 systems rather than designing 1. And so where we were able to, we did FEAs and we did calculations. For the ramp, I did like a cantilever beam calculation to determine the thickness, but some of these were probably a little bit too thick. You notice it when you're actually manufacturing how thick these are, and some of us do not have a lot of manufacturing experience, including myself, with all of these different types of components.
Was there any thought to tie into the existing battery system of the golf cart rather than having a different external battery? Did y'all encounter any challenges there?
Yes, so we did. They got a new golf cart, and that was a decision early on in the design, was which golf cart are we going to use. We ultimately decided not to tie into the existing system. That way, if they did want to move it to the new golf cart or different system, that they wouldn't have to deal with all the electrical. It's just one unit, you unbolt the frame, move it over, rebolt the frame, and you're good to go. And it also, if this just was a wash, right, it just didn't work at all, we didn't screw up their electrical system either.
That would also work better because we did not have access to the cart for a majority of our time that we were working on it. We only had about a week and a half, I believe, 2 weeks around, where we had access to the golf cart at ASU. And so if we were trying to incorporate the electrical system into that, that would have been much more difficult for us as well.
Any other questions? Thank you all.